This video is about probability, lotteries, to bet or not to bet. We're dealing with lucky numbers, we call the Mathsland lottery, and looking at the Monty Hall problem. You'll have greater understanding of probability and able to pass it on to your learners by the end of this session.
So welcome everybody. We're so happy to see you. It's 3 o'clock and I'm Tony Bearden, who started AIMSEC, and I'm co-presenting with Caroline, and unfortunately Kwatemba, who was on this slide here, who was going to be our co-presenter, has problems with electricity, and so he's not able to join us. He's moving to some other location and will perhaps join us later. We hope so.
And I'm Caroline, I'm founder of Bubbly Maths, and I am passionate about helping young learners become lovers of mathematics, to increase their skills in mathematics. And the best way to do that, I work with AIMSEC, I've worked with AIMSEC for 12, 13 years now, so that the teachers have the skills to make that happen.
Yes, we use this word empowerment, and that is our gift to you, to make you more powerful every day in what you do. Now, today we've called this, with some little thoughts about Shakespeare, to bet or not to bet. Betting, of course, is a lot more than just being. It's about lucky numbers and the Mathsland lottery. It's about probability, which is what we teach in school, and gambling, where you take a risk and maybe you put your money on it. And let's go on then. Let's get started and see what we've got on store for you today. Now, it's always our aim is to improve skills, knowledge, and understanding. And it's all about probability today. That's the key, that's what it is. And now, in particular, in order to work out a probability, you have to list all possible events, not missing any of them. And that's called the sample space. And then we'll be thinking about how we calculate the chance of winning in games, and we'll talk about some particular games. And then if it's being done as a sort of a business by a company who are inviting you to pay some money, it might be insurance, for example, taking out an insurance policy, and we have to do that when we are running a car, for example, or whether we're betting on some sport or buying a lottery ticket or something like a raffle ticket to support a charity. What is the expected profit of the organizer? That's what we'll be looking at. We'll think a bit about how lotteries are run on the very small chance there is of winning. And then something called the Monty Hall problem, which you will find, I promise you, you will find that intriguing, not easy, but intriguing. Now, we always talk about the learning spiral because we are thinking about learning as an experience for life, lifelong learning from, well, the day we're born, or before, actually before, but the day we're born, certainly, till the day we die, for most of us. And that is what makes life just so interesting, because there's so much out there, so many new things to learn. And we keep coming across, when we're on this spiral pathway, as we get older, up and up, we keep meeting things that we've met before on the same topic, and now we're adding to what we know already. And so what you see is depicting the school years, where the children come in at 5 or 6 years old, and then we're going to be talking about what happens in primary school and secondary school. And the ramp at the top is where the young people, the young adults now, are launched into adult life. And of course, further learning, even if it's just from life experiences. Well, I shouldn't say just, because that's important, but possibly in relation to higher education or an apprenticeship for a job. Now, here we've numbered because we're going up as we do, as we think of teaching in early years and primary, secondary, and then beyond. We're going to go up, and in this list, you see, we're going to start with talking about a starter activity, which is a very easy one, a game that can be played with very young learners, even preschool. And then we're going to be talking about other games and playing the games. And we're going to ask you to join one of the teams and be part of a game. And then we'll be listing all the possibilities of the numbers. They're going to be numbers that will come up in the game. And then tree diagrams, how we use those in working with probability. And why we're doing it, that's the learning objectives. What's it for? Why does your CAPS curriculum in South Africa require you to teach certain things? In particular, why teach probability? And so we'll be thinking about the learning outcomes. The learning, well, there should be outcomes if the objectives are met. We'll be thinking about the learning objectives. And then we come on to, in number 6, we come on to the 6 numbers from 49 game, which we call the Mathsland Lottery. But actually, the Mathsland Lottery is very like some national lotteries, where indeed there are 49 balls in some of them. And we'll talk about that. And thinking about using a tree diagram, but not actually drawing it, but actually using the same method, but thinking about the tree and which branches we would be writing on if we were working out the probability, but not actually having to draw the tree. And then in the Monty Hall problem is your chance to win a car. Well, at least in your dreams.
It will show you about how this game works. We don't have a car for you.
We don't have 2 rand to rub together, do we, Caroline?
No, we
don't. And then there's the Monty Hall version of Lucky Numbers. So Lucky Numbers is the simple game we're going to play earlier. And then we're going to talk about the Monty Hall version of that, which is a sort of, yes, it's just a bit of fun.
But if you do ever get a chance to play this game, you will have a lot greater chance of winning after this workshop.
A discussion on gambling in the summary, and that's all for today. But it's going to be, well, it's going to be an interesting, we hope we're trying to make it an interesting session. We are going to be playing some of these games. I want to introduce you to 4 Lucky Numbers games. So first of all, there's the 1 in 4 game, and you just need a spinner there. It's made with some paper and a drawing pin and a paper clip, and so that you can randomly choose numbers 1 or 2 or 3 or 4. And when you would choose a number first, then you spin the spinner and you win a point if your number comes up. Now, for very young children, that's quite an exciting game. I mean, not to go on and on playing for a long, long time, but to count their points and see if they can beat somebody else. Now, every time they choose a number, they've got a 1 in 4 chance of winning. So they're going to learn, doesn't need anybody to explain it. It's really just playing for fun. It's free play with very young children, but they will understand intuitively that they have a 1 in 4 chance of winning. And what that means is for every 4 spins on average, they'd expect to win once. Because it doesn't mean to say that it's going to work out exactly like that. They may be very lucky and win 4 times in a row and then feel that they're on a winning streak or something. But they will be learning by playing this game and games like it, that the sort of idea where there's equal chances of various outcomes. Each one has the same probability. And then the second game for young learners is the 1 in 6 game. And it's exactly the same sort of game, but here now we've got a different spinner, and you could use a die, a standard ordinary die for this, and you win if your number comes up. So everybody is playing, and it can be as many people as you like. Everybody chooses a number. Caroline, have you got a 1 to 6 spinner there?
Not a 1 to 6 spinner. No, we agreed I thought we agreed that we'd do.
Oh, you've got 6 cards.
Demonstrating a different method. So I've just got a little basket here, and I've got 6 cards with the numbers 1 to 6 written on them. Nothing fancy whatsoever. You can use a bowl from the kitchen, and 6 bits of paper with the numbers 1 to 6 written on them.
Yes, so the spinner's nice to have it, but you don't need to have a spinner or a die. Okay, so everybody choose a number.
Any number from 1 to 6.
Then Caroline will pick a card and we'll see if you've won. I'm going to have a go at this. I'm going to choose a number.
Okay, Antoinette's chosen 5, Palessa's 2. I've chosen a number as well. I'm drawing it out of the hat, but I'm not influenced. I can't see the numbers. So
right, come on, we want a few more people.
Ready. Oh, more people. Oh, I'll have to pick another one.
More people.
That would have been Tony. That would have been Tony, but sorry, Tony.
No, come on. It's just, if you find the chat, it's at the bottom of the black bar, and you have to take your cursor down there and click on the chat and type at the bottom.
Put mine as well. I'll put mine as well.
Oh, there's a few more. Okay,
hold on, Tony, don't do anything. You need to start sharing again somehow. I didn't realize other people can accidentally screen share, so can you start sharing again, please, Tony? Don't say anything so I'll have to take this part out of the recording.
Can you see my screen now?
Yeah, we're good again. Thank you.
Okay, Caroline, now you can draw the number.
Okay, I'm drawing a number, and it is number 6. So if we had been gambling or playing, who would have won? Let's see. We've got John. John is the only one who.
Oh my goodness! Well, there could have been several winners, but you see, this is a very simple game you can play with any age group, even very young children, and everybody can keep score. You can spin 10 times and see if anybody gets 10 points, and they can choose a different number each time if they want to. So, but it does give you the idea of an experimental probability and your chance of winning. And then there's the 2 in 6 game and the 3 in 6 game, and we're going to come on to talk about them in more detail.
Right, so
this is the game we've just been playing, isn't it, Caroline?
This is the one we played the 1 in 6. So 1 in 4 is the same game, but only using 4. And you can see if you use a spinner, that's a lot of fun for them to be able to flick it. And that's just using a paper clip and anything that you can. Sometimes I just use a pen or a pencil and stick it in and just flick the paper stick with a paper clip around it. So it's a very simple game. We always want something for the early years to be able to do. That's going to be the first step to, well, the very first step is things that they do even before they're conscious of it. But this will be the first game that they might play that will lead them towards an understanding of statistics. Just play for fun, purely fun, but it's the very first stepping stone. If they've never played a game like this and they come up to more complicated games, then they are missing that step, and they have to make a bigger leap to get there.
Right, so we need to move on. The lucky numbers game here is a bit different. You've got 6 balls, but this time we're going to be choosing 3 numbers, and they are chosen at random. And in order to win, it's much more difficult to win. You have got to have all 3 lucky numbers, not just one number, but all 3 numbers. And that's what happens in a lottery. This is a very simple lottery. So get a ticket with 3 numbers written on it if you're buying a lottery ticket, and you win a prize if your 3 numbers in this lottery match the 3 numbers on the chosen balls. And we're asking, what is your chance of winning a prize? Okay, and if you find this problem difficult, and a lot of people do when they first try to work out this probability, we suggest you try a simpler case where only 2 balls are chosen from 6 are the lucky ones, and your ticket only has 2 numbers on it. And that's a little bit simpler to think about. And so what method would you use to show that the probability of winning the 2 in 6 lucky numbers game is 1 out of 15? Note that the order in which the numbers come up isn't relevant at all. So what we're going to do is list them as pairs of coordinates, like we do, well, with coordinates. So there's no order though. So 1, 2 is the same as 2, 1 in this listing. Now, what would the possible choices of 2 numbers be? So obviously, this is the first line of my list. That's not all of them. But how would the list go on? What I'm doing is I'm listing all the possibilities. So I can have 1 with 2 or 3 or 4 or 5 or 6. So what else could I have that I haven't listed already? What do you think? Okay, well, if I give you that line, maybe you'll think about what the next line is. So you see, we've had all the combinations of 1 with other numbers, but we haven't, well, on the top line, we've only got 2 combined with 1. We haven't got it combined with any other numbers. So the second row shows us 2 combined with all the numbers. It's already been in the top row with 1, but it has to be listed 4 times with the other 4 numbers. So now you should immediately beginning to think, well, what's the next row likely to be? What is the next row likely to be? So you see, we've had 3 listed with 1 and 2, but what about 3 with the other numbers? There you are, we've got to have 3 with 4, 5, and 6. Have we got all the numbers so far, all the possibility pairs of numbers so far? Now remember, it doesn't matter which way round they are. So for example, 3, 5 is the same as 5, 3. So so far, do you agree that you've got all the numbers that have, all the pairs that have got 1 in them, all the pairs that have got 2 in them, and all the pairs that have got 3 in them? But have we got all the pairs that have got 4 in them? There's 2 more. And have we got all the pairs that have got 5 in them? Now, if you look up from here, oh, I inadvertently showed you. If you look up from here, you've got 5 with 4, 3, 2, and 1. So you need 5 with 6 to complete it. Now, if you count how many there are there, there's 15. 5, 4, add 3, add 2, add 1 makes 15. And they're all equally likely. So there is a 1 in 15 chance of winning. Now notice this is the 2 lucky numbers in 6. And we've listed those now because it's a simple case, and this is a good technique. It's a good habit of mind when you have maths questions to answer. If you can't answer the question that you have been asked, then think of a simpler question. And we were asked about 3 lucky numbers in 6, and we thought, well, we start with 2 because that'll be simpler. Now, just as I've listed there all the combinations of pairs of numbers, what about triples of numbers? Combinations of 3 numbers. Now, what you see there is a systematic listing. I didn't just list them as they came into my head, or as you might, but I actually listed them in a special order, so I systematically, so we knew we had got them all. So think about how you might do this for 3 numbers. Okay, but we're also going to look at another way of thinking about this problem, and Caroline's going to talk about it.
So it's, instead of listing all the numbers, we now know that there are 15 possibilities. So the first thing that's going to happen is you're going to pick one number, out of 6. Now we're going to put the winning stretch on the high road. So for the first section, there you go, you've got the high road. So what is the probability of the first one? Just, you've got the first number match and the first number doesn't match. What is the probability of the first number matching and the first number not matching? Because you'll put that at the end of that, between the first two, between the two sections.
We want to know the probability of matching and it not matching, and you put those 2 numbers on the first branches that you see.
Yeah. So the first one is, it's choosing 2 from 6. We're choosing 1 at a time. So the first one, you have 6 balls to choose from. Oh, that's okay. Yeah, you've got 2 chances of getting it right the first time out of 6, and you've got 4 chances of not getting it out of 6. Now, the second section, we've only got 5 balls left, and there's only, in order to win, to go completely across the high road, there's only 1 left of the winning balls and the winning numbers. And so you've got a 1 in 5 chance now of winning the second dip. And you can see all the probabilities of the others. And what you're going to do then is the probability is 1 in 15. So it's 2 out of 30. You multiply those 2 together because you're doing both, and they are, one is conditional on the other, so, or changed by the other. So the probability is 2 over 30, or 1 in 15 of getting that, succeeding in getting both answers.
So that's the same as when we thought about counting all the possibilities. But if you think about it, and if you're working with learners about doing this, you see, in the first of the, what Caroline calls the high road here, there's 2 lucky balls out of 6. So that's your chance of winning. Now, then there's only 1 lucky ball left to choose. And 4 out of 5 times, your choice will be the wrong one. It's only 1 out of 5 times, or a fifth of the occasions, that your choice will be lucky. So so when you've won the first, you've got the first number right, only 1 in 5 of the times will you get the second number right. So that's why you divide by 5 or multiply by 1 over 5. And then you complete this tree diagram in the same way as we've just been describing. So you've got a 4/5 chance that your second number doesn't match. But why is it 2/5 here? If you didn't pick the lucky number out in the first pick, or Caroline didn't pick your number out in the first pick, then there's 2 numbers now still in the bag, or the box, that are lucky. And out of 5 numbers, you have a 2 in 5 chance of winning here, that your second number's lucky if your first wasn't. And 3 times out of 5, you won't have a lucky number. And so
I'm responding to a comment, Tony. Remember that we've got 2 chances. We need to get 2 winning numbers out of 6. So the first one is the 1/3. There's a 1/3 chance, or a 2 out of 6 chance to pick the first lucky number. Just making that clear. I'm just looking at a comment on the chat.
Now, when it comes to the 3 and 6 game, we're going to actually have everybody playing. Okay, so but this time I'm hoping that you've seen this shown to you, the solution, and I think most of you have met it before anyway. This sort of thing, you're seeing it as possibly counting all the possibilities or possibly using a tree diagram, and you're going to get the same answer. Of all the tickets that there could be here with 2 numbers on them, there are 1 in 15 will be winning numbers on average. Now I'm going to ask you to think about the listing, and we listed all combinations for 2 numbers chosen from 6. So what about listing the combinations for 3 numbers chosen from 6? Would you like to think about how you would do that? You should have a pencil and paper handy. I hope you have. You might like to start making a list. 1 and 2 can come up with 3, 4, 5, or 6. But those are the only ways that both 1 and 2 can occur. But I'm going to show you little by little all the rest of the possible combinations in this, listed in this sort of way. Why don't you try to get ahead of me, and on your paper to write down the next row. And I'll pause each time to give you a moment to do it. What do you think the next row would be? We've had 1 and 2 with all combinations. So the next one is 1 in 3, which already occurred with 2, but it can now occur with 4, 5, or 6. So can you write down the next row and see if you can write this down yourself and keep 1 step ahead of me? What do you think the next row will be? Now we've got 1 and 2, 1 and 3. Yes, the next row is 1 and 4 with the other numbers that it hasn't already above, on the 2 rows above, been given with. It's already been given with 1 and 4 and 2, and 1 and 4 and 3, and now we've got 1 and 4 and 5, and 1 and 4 and 6. What's left that we haven't got, which includes 1? It's 1 and 5 with 5 and 6. Now that's all very well, but we're not there yet. We haven't got all possible combinations because we want to have the combinations. Now write the next row down. What do you think it's going to be? It's following this same pattern, and a lot of maths is about spotting number patterns. Can you spot the pattern here? Write it down for yourself. So we've had all the possible combinations with 1, and the next row is not with 1 anymore. We've got 1 with 2 and 3. Sorry, we haven't got 1. We've got all the possible combinations of 1 above, and now we've got we're listing all the possible combinations with 2. So we've got 2 with 3 and 4, 2 with 3 and 5, and 2 with 3 and 6. Notice it's 2 with 3 and another number. So what's the next row? Write that down. Make it, do your best. If it's wrong, it doesn't matter. You're the only one who's going to know. Yes, it's 2 and 4 with 5, and 2 and 4 with 6. Okay, so what else do we need to put 2 with? We haven't seen already 2 with something. The curves above the triangle of patterns of triples above, when one's, and now what, 2 with what? 2 with 5 and 6 is the last one. We're listing quite a lot of them. Now, I think we've actually dealt with 1 and 2. We've got some combinations with 3, but what's remaining? What haven't we got that has a 3 in it? What do you think the next row is going to be? It's 3 with 4 and 5, and 3 with 4 and 6. And there's just one missing combination. What is it? With 3. And then there's another one. So there's two more. What do you think the final two are? There's a missing combination with 3, and then there's one more missing combination to list. Can you write those two, the last two, down for yourself? And then if you've got them, pat yourself on the back, because we still needed 3 with 5 and 6. And the remaining one that we hadn't yet got was 4 with 5 and 6. Now, who got that? Did you understand it? Did you manage to keep a step ahead of me most of the time? Now it says, yes, so Noxola wrote 4 with 5 and 6. That was the very last one. Well done, well done. Yes, so if you count them, how many are there? How many possible outcomes for 3 numbers chosen from 6? So one of these must be the winning combination. And there are 20 of them, so there's a 1 in 20 chance of winning. Still a fairly good chance of winning here, but a little bit less than with the when you only had 2 lucky numbers in 6. Now here we remember that we had, it's up there on the left, we had a tree diagram when we had just 2 numbers in 6. And we've got to imagine for the 3 numbers in 6 game that we've got a tree diagram like the one that's drawn in the middle there. But we don't need to draw the complete tree diagram. All we need is just the branches at the top, where all 3 chosen numbers are winners. There, those 3, that's the high road, as Caroline called it. Now, those are the branches where, so this branch, the first one here, this one is for the probability that the first number that's chosen is yours. It's one of your numbers, so it's a winner. And then this branch is where you put the probability that already you've got 1 winner, so you're beginning to feel very hopeful. And then when the second number is drawn, the probability that this second number is also one of your numbers. So now, if you're coming along here, you've got 2 out of the 3 lucky numbers. Now, what's your chance that on the third draw, which is this branch of the tree represents, that's the third number, and you've got 1, 2, 3 lucky numbers, and you win. Now we know, because we've just listed all the possibilities, we know that that chance is going to be 1 in 20. But how does it work out by this method? The method which is similar to just writing 2 over 6 times 1 over 5 for the 2 in 6 lucky numbers game. What would we write on these red branches here? So what's the probability of winning the 3 numbers with 3 numbers in the 3 in 6 game? Your lucky numbers being the numbers. Okay, so let's play it now, Caroline. Now what I want you all to do is pick 3 lucky numbers that you are picking, any numbers between from 1, 2, 3, 4, 5, or 6. Just commit yourself to a little gamble here, flutter they call it. I'm going to put down, they can't be repeated. I'm going to put down the odd numbers, 1, 3, 5. You're not going to be sold a ticket, you're going to choose your numbers this time. Just any 3 numbers, it doesn't matter what they are. You're not answering a question. It's not right or wrong. Any 3 numbers. Now, Antoinette's done the even numbers. I've done the odd numbers. They don't have to be special numbers. Any 3 numbers between 1 and 6, without any repetition.
Drum roll, everybody, wherever you are. Give us a
Come
drum
on,
roll.
this is a very tense moment. Who's going to win?
What? I wanted a drum roll. Right, okay. Right, here's the first one. And the first one is 2. Oh, I'm in with a chance. The first one is 2. The second one, okay, there was a 1 in 6 chance of getting that one. There was a 2 in 6 chance of getting that one for me because I won. No, anyway, it was 3 in 6, wasn't it, on that latest one? And the next one is 3. That's 2 and 3. I'm out. And the last one is, see if any of you are getting excited, 6.
Does
So the
anybody
winning
get
combination-
2, 3, and 6? Was there a winner?
Yeah.
Was
Yes.
there a 2, 3,
Yes,
and
me. Me.
John,
the
you got
second
2, 3,
time.
and 6.
That's
Oh.
the second time John's won. And what are the chances of that, Tony?
I'm going to have to buy a lottery ticket
I
tonight.
think so. Yeah, you've got a great chance of winning. No,
So because there were 3 lucky numbers in the box, the chance of the first one being one of your numbers was 3 and 6, and then had you already got a lucky number, which John had, the chance of the second one being lucky was 2 in 5, and John was then thinking, "Ooh, I have a chance here. It might be, I might get this." And then the last one, of course, there were 4 balls still in the Caroline's box, and only 1 was John's number, but that was picked out. So 3 out of 6 times 2 out of 5 times 1 out of 4 is 1 in 20.
This is a very rare event for me.
John's a winner.
oh well, the one time that you don't get a prize, you win. Just to let you know that we've had contributions from partners as well. Somebody's husband has made a guess, so do feel free with these calls to include
yes, anybody in your household who wants to join
Yeah.
in is very welcome. Okay,
Yeah.
so now we're going to think about lotteries and other gambling and how the people who actually run it, or run the casinos and the other gambling, how it's set up so that they're never going to lose. Well, they will lose sometimes, but on average, they're always going to end up making a profit, and they are going to get rich by the fact that other people are losing money. So let's look at a very simple example here. If 100 people play 10 Rand to play the 3-number game, which we've just played, and the prize is 150. Well, that's quite good, John. You'd have paid 10 Rand and you'd have won 150. So that's quite nice. Would the organisers expect to make a profit? And if so, why? What do you think? So it's the 3 numbers game that we're talking about, 3 numbers in 6. Just give you a moment to think about that. So do the arithmetic, work out how much they'd expect to collect, with what people would pay for the tickets, how many prizes they'd expect to award, what that would mean in terms of payout, and how much profit they would expect to make. Let's think about this. If 100 people pay 10 Rand, then the organisers are going to collect 1,000 Rand. Now, the expectation is that there would be 1 in 20 of those tickets would be winning tickets. And 100 people have actually entered. So that's 1/20th of them would have had winning tickets. And so that would be on average 5 winners. And so 5 winners, each winning 150, the organisers would pay out 750 Rand. But they collect 1,000 Rand and then make a profit of 250 Rand. And actually think about it. If the tickets cost more than 7 Rand 50, then the organisers would make a profit on average. And they actually are going to charge 10 Rand, so they're certainly going to make a profit on average. That doesn't mean to say that's what's going to happen every time they play the game, but then playing it frequently, the the organisers are always going to end up making a profit out of this. But some people are going to win, so they're going to be the lucky ones. So Caroline,
Yes.
I think you want to tell us a bit
Yes.
about why do all this? What are the learning objectives?
So there are two areas: being systematic and having useful tools. We're looking to systematically order all the possibilities. We want to make sure we've included every single possibility. So being systematic is critical to be sure that you've got them all in the way that Tony did it with the rows and columns earlier. And so we want to both get practice. The objective is to both get practice and learn how to use these methods, but also to actually, by using the methods, find out the complete sample space, find all the possibilities. So using the tree diagrams, once we know how many possibilities there are, we then use the tree diagrams to work out the probability of winning. So use them both, but I find it useful to have the systematically ordered list before doing the tree diagram myself. So the activity can be used in different lessons for different learning objectives and for different age groups and different attainment groups as well. And you just choose it according to the class that you're dealing with. And for older learners, the teacher can combine both. You can use both for older learners.
But I think the thing to think about here, there's learning to be systematic in your planning is hugely important, not just in the maths classroom, or not just in applying the maths, but in life in general. But actually, if there were a much larger number of balls and a much larger number of possibilities, we wouldn't want to use that method. We would want to use the tree diagram method. But the point of doing this, Caroline has just explained, is so our learners understand both methods. So by understanding them both, they'll have a good understanding of these sort of basic ideas of probability. So this is why we would have them do it. The class can play the game for fun, and then they can collect data from the whole class, and they'll find an experimental estimate of the probability of winning and learn the difference. Now, this is important, to learn the difference between experimental and theoretical probability. Now, in this case, we're going to be able to work out what the true probability is, the theoretical probability. But in many aspects of life, there's no way of knowing other than by doing a survey or an experiment there's no way of knowing what the probability is. I mean, if there's an election coming up in my country in May, nobody knows how the people are going to vote, but people are going out to do surveys asking, are you going to vote for this party or that party? And counting the answers, that's an experiment, and they're getting an experimental estimate of the probability of the different possible votes, okay? And in a medical trial, that's what they do. They have a treatment, and they have a tablet that they make, say it's a medicine they're trialing. They have the tablet, that's the really new medicine that they hope is going to cure this illness. And then they have just a powder that's maybe sugar or something, and is not actually any curing properties. And people who take these tablets don't know which ones they've taken. And thousands of people have to be involved in these medical experiments. And as a result, they get just an estimate of the probability.
And Tony, just to comment on the amount of samples you have to take, doing this activity as an experimental activity, you might find the numbers are completely off. Like Tony and I played a game last year on one of these sessions where Tony won every single time, even though the chances were that I was supposed to win. I had a better chance of winning than Tony, but I never won. Tony won them all. So if we did it by experiment, we would think, oh, the chances, Tony has a better chance with winning with her circumstances, and it just wasn't true. So doing this as an experiment and then actually working out the proper sample space using the methods here is a very valuable learning activity.
That's right. And the point here is of talking about it, as we just did, is that when you're teaching your learners, it's important that they understand that in real life applications of the maths you're teaching them, there are two sorts of probabilities and both are important. And we often do this experiment when we actually can work it out theoretically. But indeed, there are many other situations where, you know, you might be speculating about what the favorite food is of the members of your class or the school, and you could do a survey, and then you could draw some graphs, this would be, supposing you think, well, I think that the chance of the favorite food being chips, okay, just chips. If we have a list of things, what's your favorite food? The majority of people we ask are going to say chips, not everybody. And then you could do an experiment and see whether that's true or not. There's no way you can do that theoretically. See what I mean? So that's a different sort of condition. So this also offers a simple case of a lottery type game to help learners to develop an understanding, and then we're going to build on it to work out the probability of winning the national lottery. And then they're going to discover how little chances of winning the national lottery. And then we're going to think about how you might discuss with your class the concepts of risk, insurance, when you take out an insurance, gambling, and the advantages and disadvantages, the benefits of these things. Now, so the Mathsland lottery, now we're getting a bigger lottery. We're going to can think about 49 balls, and they're numbered from 1 to 49. And this time we don't need to be choosing just 2 or 3 balls. 6 balls are chosen at random without replacing them. There are 6 different winning numbers that are chosen. If it's done, you know, maybe it's going to be drawn on Saturday at the end of the week. So it's 6 winning balls out of 49. So each lottery ticket has 6 numbers, and you win a top prize if your 6 numbers are the ones that are chosen that week. And what we're going to ask you is, what's your chance of winning? Now, I'm going to tell you that your chance is 1 in 14 million. And that's a very, very small chance. And we're going to think why that would be so. And what it means is that if I buy 10 tickets a week, it could still be thousands of years on average before I'd win a prize. Now let's see why it's so low. Now I'm going to carry on, Caroline, because I want to because we're just running. Want to give you something to do.
You were very thorough with this, Tony. That's just.
We want to have a break. And we want to get to a certain point to give you something to think about during the break. Now, all I'm doing is reminding you of the list we just made, okay? I'm going slowly through it, but you've seen it before. So remember what happened with the 3 numbers in 6 game. Now, that's one reminder. Now, the next reminder is, think about it. Think about the tree diagram. We also use that.
Now, wait a minute, Tony. You're talking about 49 balls. We have to write out a tree diagram for 49 balls and all the combinations for 49.
No, well, Caroline, I wouldn't like to do that. It would be such a, well, you need such a big piece of paper and it would be so difficult to do it. So, but what we've got to think about is what we did with 3 balls. And remember, we only went along the top of the the top line, as it were, because all to be a winner, all the balls, we were looking for winning the jackpot. It's a bit more complicated if you are looking at a prize. What's the probability of a prize of 5 out of 6? It can be done, and it's not that difficult. But what we're only going to talk about winning the jackpot, which is having all the 6 lucky numbers. And because
okay, so it's more of an intellectual exercise. So we can look at, if you take the high road to win all 6 of them, can people start working out what they'd be? What's the chance of picking a ball the first time and the second time, going all the way through to 6
It doesn't. There's, although there's 49 balls in the sort of frame that's used in the lottery, and in our case in your box, Caroline, okay, you only pick 6, so you only need not 49 branches but 6 branchings, which means 1, 2, 4, 8, 16, 32 ends on your
and we're
diagram.
only interested in the big winner, so we're only interested in the high road, if you win every single time, so you've only actually got to work out one path.
Yes, that's right. So in fact, remember what we did with the 3 numbers in 6 game. This is just reminding you we've already done that. Now when we come up to the 3 numbers in 49 game, then the tree must be extended 3 more times, showing the 6 choices. That's what we were just talking about. And now let's think about the first number. The chance that the first number wins is 6 out of 49. If we've won with that first draw, and that's along the top of the tree diagram, remember, those branches that we made red for you. If we won the first time, then there's only going to be 5 winning numbers left out of 48. So the probability that both my first and second numbers win is 6 over 49 multiplied by 5 over 48. So now, and this is for the break, and now we're going to give you a break for 5 minutes, and we'll start again at 3 minutes past the hour. The question is, what is the probability of winning the top prize for 6 balls chosen from 49? Now I've started off that calculation for you, but you've got to sort of extend it a bit. And if you've got a calculator, you might like to work it out for yourself. Now, because there are 6 lucky numbers, 6 balls with the lucky numbers to be drawn, there are 6 fractions to be multiplied together to get this answer. And each of those fractions is the probability of that draw. And what you see on the screen now is 6 over 49 is the probability that the first number that's drawn is lucky, is one of your numbers. It is a lucky number, but is it one of your numbers? Then that probability is going to be 6 over 49. And the probability for the second one, if you've already got one lucky number, is 5 out of 48. Now, given that you've already got the first 2 numbers are lucky, and you're getting quite excited because everything's going your way, is what's the probability that the third one and the fourth and the fifth and the 6th draw will also be drawing out of the system, whatever it is, will be drawing your numbers. Okay, so then let's move on and think about what that probability really is.
We've got 2 answers in the chat, Tony. Pam and Antoinette have both come up with your same conclusion.
Okay. So yes, it's 13,983,000. Okay, so it's 1 in 14 million. And let's see those 6 fractions on the top. 6 over 49 times 5 over 48 times, now 4 balls left out of 47 they've already drawn 3 of your lucky numbers, and the 4th one then is also lucky. And if all that's happening, then there are 3 numbers still to draw, and 46 of them are still there, still in the bag or the box. And so it's times 3 out of 46, times 2 out of 45, times 1 out of 44. And if you do work that out, you get 7.15 times 10 to the minus 8. Now you may wonder how that turns out to be 1 in 14 million. To see why this probability, 7.15 times 10 to the minus 8, is 1 in 14 million, compare it to the probability of 1 in 20. Now that is the same as 0.05. If we're going to say the probability is 1 in 20, equally well, we could say the probability is 0.05 or 5 over 100. Now, for this probability, let's see, it was 5 over 100. So let's look here for what power of 10 we've got. This probability is 715 over 10 to the power 10. So now let's turn that round as we did with the probability of 1/20th by dividing 100 by 5. Let's divide 10 to the power 10 by 715, and we get 13.986 million to 3 decimal places. So in fact, what we've just argued is that this probability is 1 in 13.986 million. So we just round that to 1 in 14 million. And there are 52 draws each. It's only 1 ticket a week, and there are 52 weeks in the year. So there are 50 draws in the year. So you divide by this number 14 million by 50 for each year, and then you find that it's 270,000 years. Now, of course, you might be lucky and win next week. That's what happens with probability. It's not very likely, but it could happen. Yeah?
Well, it's definitely going to happen for one person here today.
Well,
that
Caroline, that's very optimistic of you, because what actually happens with the National Lottery is sometimes nobody wins that week, and the prize is carried over to the following week.
Yes, but some of them roll over, and some of them,
but that when they roll over, eventually the money and it will be more than usual if it's accumulated, if it's rolled over for 2 weeks. So
and I was thinking about John, since he's won twice, you know, he'll definitely win
right.
it.
Oh, okay. No, he's very lucky today. Okay.
So
now
the UK lottery is even worse. The UK lottery has 59 balls. South Africa's lottery has 52. So again, it's worked worse. You're all right in Spain, Pam, 49 balls. You're still good at 1 in 14 million. And that's for the jackpot, of course. The jackpot is getting all 6 balls correct. There are other prizes that are much less significant if you get match 4 or 3 or 5 balls. But the question that we're asking, and the question that we encourage you to ask your learners, this is part of life skills, is, are there better ways of spending your money? The way I view it, having said that, I haven't actually ever bet on the lottery. There are 2 things. One is our lottery at least goes towards some good causes. There's a lot of excellent things that the National Lottery funds get spent on. People can apply for bursaries and things. And also, my mother-in-law always used to say, if only I had put aside all the money I spent on the lottery, I would have a nice little nest egg by now. So perhaps encourage putting the money aside and investing it in some way, in a realistic way, rather than hoping. And that's for 49 balls, hoping against all odds that you'll be that 1 in 14 million. And sometimes nobody wins. So the chances of winning then is 0.
So there's some of the lottery, some countries have several different lotteries, and there's Euro lotteries as well that everybody in Europe can participate in. But Spain has, I don't know, got 5 or 6 different lotteries. There's one where you have 5 balls in you have 6 balls in 49, and then you have an extra ball, which you don't win unless you win the 6 balls in 49 and this extra ball, which is sometimes called a bonus ball. So there's all sorts of complications, but the principles are always the same. You may have to take into account, well, you will have to take into account more branches of the tree if you're looking for what's the chance of winning 5 balls when there's 6 drawn, but what's the chance that your ticket has 5 of the 6 on them? Well, you have to be looking at more branches of the tree. So it does get a little bit more complicated, but not much more complicated. It's just you have to take into account more possibilities. So let's move on to the Monty Hall problem. So I'm going to explain it, or Temba was going to do it, but he's not with us. So I'm going to explain it. And then Caroline's going to have another a few more ideas about it. So this is a very, very famous problem. If you just Google it, you'll find there's a lot of information about it. It was a quiz show in America originally, and Monty Hall was the host or quiz master. And it was a very popular show because when they ran it, somebody would win a car, okay? So this is how it was. It seems so simple. You wouldn't believe how simple it is, but people get tied in knots when they think about it. And let's just see how it works. You know, let's think about it. There are 3 boxes. Now, one of those contains a super sports car, and 2 contain goats. Okay. Now, who wants a goat? Well, maybe you do, but you'd rather win the car, I'm sure. Now, you have to choose one of the doors. All the 3 doors are closed, and behind those doors, you know there's a car behind one of them. Now, you choose the door, let's say you choose door 1, but you don't open it. Monty Hall opens one of the other doors to show you that there's a goat behind that door. So you know that that's not what the door you want, because there's only a goat behind that door. So he's shown you something. Now, you know that the car is either behind door 1 or door 2. You don't know which one it's behind, and you've chosen door 1. Should you change? Should you opt to switch to, to say, no, oh, I want door 2 now. I'm going to change my decision to door 2. Should you change? What does probability tell you? Should you stick with door 1, or should you change? So why don't you think about that? Why don't you put in the chat, stick or change? Should you stick or change? Or actually, we could do a yes, no, yes, I would stick. Or should you change? Yes, I would change. Thumbs up. No, I wouldn't. Thumbs down. So if you were doing this in your class, then you would probably ask for thumbs up, thumbs down. Now, I would only do it if you've got some really kids who were very confident about probability, because it's a bit tricky. But I certainly might have a go with grade 11 or 12 doing this. Younger children will understand what the game is, but they won't necessarily understand the subtleties of the probability. But it's simple. Let's see, maybe they would. You should have the option. You do have the option to change. Now let's look at some diagrams here. At the start, the probability that box 1 contained the car was a third. Well, surely we all agree it's a third. There's 3 doors, equally likely to have a car behind any of them. So the chance that your door, number 1, has the car behind it is 1/3, and that doesn't change. Given the extra information, and we know the probability that the unopened box contains the car is 2/3. And why is that? So you should change your choice. Now let's look at why it's 2/3 in this diagram. So the 3 possibilities are shown there in 3 bands, okay? And on the left, you see the 3 possibilities for door number 1, and they're given in yellow. So when you open the door, the light behind will show you either a goat in 2 out of the 3 cases or a car in 1 out of the 3 cases. Now, those 3 bands each have equal probabilities of a third. That doesn't change. Now, Monty Hall will open a door and show you a goat. Now, he will certainly not open the door which has the car behind it. He'll open the door with the goat behind it. And so you know, in case number 1, which is this top band here, right, and in case number 2, you know where the car is. However, actually, it might be case number 3, in which case it doesn't matter which door Monty Hall opens. He'll show you a goat, but there's a goat behind the other door. So in 2 out of 3 cases, you should change because you know where the car is. And in 1 out of 3 cases, you should stick. But you have more chance of winning. It's not certainty, but you have more chance of winning if you change. So you should change. Now, what about your take on this, Caroline, with these diagrams?
So it's the same problem, but it looks slightly different. It's a slightly different approach. Exactly the same thing. 3 boxes, 1 contains a car, 2 contain goats. You choose door number 1. Now, you might have the car with door number 1, and you might have a goat. One of the other doors is opened, and you have an option to change the other door to one of the other doors, should you change. It completely depends on one critical matter, and that is whether the host knows where the car is. So the first time, as Tony said, the car, everyone has a 1/3 chance, but if you notice, 2 of the doors, 2 and 3, is you've chosen 1. Therefore, the chance of the block of 2 and 3, there's a 2/3 chance that the goat's behind one of those. Now, the host, remember, the host knows where the car is. So having chosen one of them is open, that means that there's a 2/3 chance that in door number 2, the car is there, because the probability hasn't changed. But it's only true if the host knows where the car is.
So Caroline, we're going to move on to our game, the lucky numbers game, but we're going to Monty Hallize it. So this version of lucky numbers is similar to the Monty Hall problem, but the probabilities are different. Now, the host picks 3 winning numbers and keeps them secret. So he knows what the winning numbers are. Okay, so we're going to demonstrate this, Caroline. Now, everybody can choose 3 numbers and show, and so, well, I'm going to do it. And I'm going to show my 3 numbers to you, Caroline. And so my 3 numbers are 2, 3, and 6. This is how the game works, right? I've shown you my 3 numbers, 2, 3, and 6. All right. Okay. Now I want you to, you're the host, all right? So you're going to choose one of the three numbers that I didn't choose and declare that to be a losing number. So you actually don't even need to draw it out of the hat unless you want to, Caroline. So the remaining numbers are 1, 4, and 5. So you're Monty Hall, Caroline. So are you going to tell me that 1, 4, or 5 is out of the game?
5 is out of the game.
Right. So this is like the Monty Hall problem with the goats. The losing numbers are like goats. So now we've only got 5 numbers. All right. So I then have the option of changing my choice of 3 numbers. Okay. Now, Caroline, could you just take 5 out of the box altogether?
It's out of the box.
Right. Okay. Now then, I am going to change because that's what you're supposed to do. And I am going to take, to change my 2, and I'm going to make it 1, 3, and 6, because changing is just because it would seem to be the right thing in Monty Hall. I'm going to change to 1, 3, and 6 now. Now, Caroline, will you now choose the actual winning numbers? Remember, we're only choosing from 5 numbers now, and let's see if I win. Caroline, 1. Oh, I've won the first number. Okay, I'm doing well. The other 2 I want are 3 and 6. The second number, Caroline? 3. Oh my goodness, Caroline. Now make sure you shuffle those. Oh my goodness. Would I get the 6? Ooh, I might.
I'm being very careful to really shuffle these.
And you've got your eyes closed.
Ah!
No! Oh my goodness, I've got the big prize. Now I am amazed because there was still not a big chance. But remember, this is not the big 49 ball lottery, and we're only talking about 20 possibilities in the first place. So anyway, that's made my day. So I think we just quickly run over that. The host picks 3 winning numbers and keeps them secret. Well, you didn't do that, Caroline. You actually drew them, but it doesn't make much difference. You know what the winning numbers are. And you know that, so you choose 3 numbers from 1 to 6 and show them to the host. And the host then chooses one of the 3 numbers that you didn't choose. You didn't choose, just like he opens one of the doors that you hadn't chosen and declares that to be a losing number. Caroline declared 5 to be a losing number. I then have the option to change my choice of numbers, and the answer is I should change. Now I'm going to.
We didn't do it that way round, but
so we didn't, Caroline. Never mind.
But the probability is the same. It doesn't matter which way round, because having extracted the 5, the probabilities remain the same.
So what we're going to do now, Caroline, is my chance of winning is 1 in 20 when we start. Because there are 20, we listed all those triples, didn't we? And what we saw was, there they are. And now, of course, we don't know which numbers are being taken out of the game, because there are only going to be 5 numbers. So there are only actually 10 combinations. When you're doing this with 5 numbers, there are only 10 combinations, and I've listed them there on the screen, so you can see. And the reason I've called them A, B, C, D, and E rather than 1, 2, 3, 4, and 6 is that this works whichever is the number that's taken out of play. And so let's go through this very slowly to see how this works out. Initially, my chance of winning was 1 in 20. And my chance of losing was 19 out of 20. But I get some more information. I'm told that one of the numbers is a loser and it's taken out of play. So 5 is no longer used at all. The number 5, in the case that Caroline and I just demonstrated. And there are only 5 numbers in play. And the question is, should I change my numbers? And this is how it works out. Now, the chance of one choice of 3 numbers chosen from 5 being the winning combination is now 1 in 10. And just in the left-hand side there's shows you that all possible combinations of 3 numbers from 5, there are only 10 of them. So now the chance of the winning combination is now 1 in 10. So by changing, and that notice that in 19 out of 20 times, my chance, which was 5% or 1 in 20 originally, is now, if I change 19 out of 20 times, I get a 1 in 10 chance of winning. So that's 19 out of 200 or 9.5%. So by changing, my chance of winning goes up from 5% to 9.5%. It's not doubled, but it's very nearly doubled, isn't it? So yes, I should change. So I'm going to go on, but I'm going to share this PowerPoint, the slides from this PowerPoint with everybody who wants them, so you can think about it a bit more. And then
Shall I do this one, Tony?
yes.
So it's what is gambling and why study probability? First of all, gambling is an activity where 2 or more parties place at risk something of value. They call it the stakes. This is in the hope, and I emphasize the word hope, of winning something of greater value. Now, the results depend on the outcome of the events, which are unknown to the participants at the time of the bet. But what is a factor in here with the gambling is that the organizer, the owner, will always win. Statistically, they're designed, the games are designed to make a profit. It's a business to make a profit for the organizers. And according to the North American Foundation for Gambling Addiction, gambling worldwide has greatly increased recently due to internet. So online gambling has caused a huge increase in gambling addiction.
And that is really a problem.
Yeah.
Yeah. Well, gambling, there's all sorts of gambling, like buying a raffle ticket to support a charity, for example. And you're not going to get addicted to that. But some
people do, but it's not, I don't think it's so much of an issue. It's more the horses, isn't it? And not so much the bingo hall, but the slot machines. But the online gambling is really worrying because it is designed, first of all, it's right in your pocket, it's right in your head, and it's available to you 24 hours a day, 7 days a week, wherever you are. And it's designed to literally hook you. They give you free games, and then slowly but surely you start putting a little bit more in, a little bit more in. They give you a little bit of money, and then they take it back, and they literally draw you in and hook you into gambling. So it's a lot easier to get addicted to online gambling because it's so easy to do.
There is and of course it goes back many thousands of years. In most cultures, there's different sorts of gambling. And there's a lot of gambling on sport. And I've shown some horse racing there. But there's gambling on all sorts of sport. People, any match, any competition, boxing, cricket, baseball, basketball,
rugby,
you name it, people will take bets as who's going to win. And of course, they don't know who the winner will be. And different people, the odds will change. Now, the
odds are determined by the bookies, and it's where the odds is where you're going to lose, is because the odds are calculated so that the organizers, the owners of the businesses, are always going to win over the long run, aren't they, Tony?
Yes. And so you see that man with his hands up like this on the top left. Now, here's what is called a tic-tac man. Now, what he's doing is signaling, he's on a race course, and he is observing the condition of the horses, and he is also listening to people around him, what they're saying about the horses and who is most likely to win. And he is passing information across to his colleagues who he's working with, who are taking the money from the gamblers who are gambling on the race. And so that's gambling on sport. Now, in the casino, where it is on a beautiful building with mountains behind, that's in South Africa. And that's a luxury hotel. You can go for a safari there. You can have a holiday there. See, there's a swimming pool. But of course, it's a gaming casino. And beside it, there's a lottery wheel. And just below the lottery wheel, there's a ticket with some numbers on for a lottery. And then you see in the middle there, you see slot machines. Now, a lot of people go to these arcades and they're called one-arm bandits, and they play on the slot machines, and they win, but and they get very excited about it, and sometimes they lose. Now, a bingo hall, they're very common, and usually people pay to play each game, or they play for an afternoon of they pay to come in for an afternoon of bingo, and then they fill in a card, and if the lucky numbers are called and it's on their card, they mark their number, and if they get a row, the first person to get a row wins. Now, that is actually quite often the only entertainment those people have, and the only way they have, so they live alone, of this socializing. So it can be quite a gentle way of actually gambling, but it's, for some people, they do spend a lot of time doing it. And next to that, there is a phone, a sort of a little illustration showing you what Caroline was saying, that there's a lot of gambling online. And at the bottom on the right, there's the football pools there, where people fill in the pools and pay for it every week. And according to who wins the football matches, they may or may not get a prize. Now, commercial gambling operations, as we've said, depend on mathematical facts. So the people who run these gaming houses or betting shops know quite a bit of mathematics, and they ensure that the company cannot lose in the long term. And these companies are not gambling, not in the strict sense, because they're not taking risks. So they have organized the frequency with which people are going to win in such a way that there are going to be people who win prizes, but they're going to collect more money that they're going to pay out. Now, of course, risk is very important to us all, and we take out insurance, whether it's health insurance or life insurance, or against our home insurance, or against something being stolen from us. We have to have car insurance if we're going to drive a car. If we go on travel and it's expensive, maybe, you know, a flight or something, we might take out travel insurance. All of these different sorts of insurance are sold by insurance companies, and the insurance companies assess the risks, and then they use mathematics to work out how much they would need to pay out if a policyholder made a claim, and because they'd suffered a loss for something covered by the policy. Suppose they needed some health care, so they claim on their health insurance, or they have a crash and they need to claim on their car insurance, and there's the other as well. Now, the insurer decides the amount to charge for the insurance, the premium, which is what you pay, so that in the long term, the insurance company makes a profit. So it's a good sort of part of education that your learners, the older learners at least, know about these operations in the big wide world, so that they don't run into difficulties themselves. And it's important they understand what's behind the principle of insurance.
So the game of gambling has been going on for millennia. and you can be sure that there were people that had their methods and their ideas and successful techniques to actually win more consistently at gambling, especially the people that organized the gambling and wanted to make the money on top of the bookies. Mathematically, the history starts with the desire by Girolamo Cardano in the 16th century, in the 1500s, to analyze gambling and games of chance. That's where it started formally, with mathematical theory of probability. And then Fermat and Blaise Pascal took this further in the 17th century, in the 1600s. And then at the end, near the end of the 1600s, Christian Huygens, not quite sure how to pronounce it, he published a book on gambling and the theory of probability. So it's a progression, just like it is with other methods, other research, it's a progression. So Pierre Laplace, in the early 1800s, in the 19th century, finally published what is now considered to be the complete basic theory of probability. So this goes back 200 years. And these historical characters are the shoulders, the giants of the shoulders that we stand on their shoulders for the development of further probability work.
So it's quite interesting for our learners to understand that what they study in school is something that hasn't always been known about, okay, or hasn't always, and this theory of probability, Caroline's explained how it arose out of gambling, and everything we teach in school, that's where the actual terms and the way we treat it mathematically all originates. So there's a reference that we'll give you if you want to look at about the probability. Now, here's a summary of what we've been talking about this afternoon. Let's look at the things and review what we've learned. And this is a good way to end any workshop or lesson, really. So we're thinking about there's many, many different sorts of gambling. And when we were looking at the game where we were choosing two numbers from 6, we listed all the possibilities, and we were working systematically there. And we had a tree diagram, and we used the branches of the tree to write the probabilities on of each event. And then we multiplied them together to get the probability of both of those events happening at the end. And there's 4 ends to the branches there. So we sort of understand that, then that leads us on to the 3 numbers in 6 game. And again, we thought about the probability of winning a prize. And here there were far more different possible outcomes. There were 20 of them. There were triples in it now. We listed the triples. We listed them vertically. Now I've listed them horizontally. And it was manageable. Once you have 4 numbers or 5 or 6, there's far more possibilities. And that's out of 6 balls. But if you then, if you're then looking at 49 balls, then that is going to be, that's the Mathsland lottery. That's going to be a lot of numbers to possible outcomes to list. And you wouldn't want to do that. And you could draw the tree diagram. So just as in this, but probably you don't need to. So in this tree diagram for 2 numbers, there's 4 ends. And when there were 3 numbers, there's 1, 2, 3, 4, 5, 6, 7, 8 ends. And each time you double the number of ends and therefore the number of different sorts of events that can happen. So when there are 6 numbers, it's 8. And then, so when there are 4 numbers, there are 16. When there are 5 numbers, there are 32, and when there are 6 numbers, there are 64. So it's 8, 16, 32, 64. And so that's how many endings there would be to the branches. But you really only need to go along the top to multiply those 6 fractions together, which we did around the break time. And then we thought about the Monty Hall question, and dreamed of possibility of winning a super red sports car, and that was quite fascinating. And then we thought about the game that we've just played, in 3 balls out of 6, and then having a sort of where there was a 1 in 20 chance, and then making a Monty Hall version of that. And we saw that if we were given some further information by the person running the show after we'd made our choice, then the chance would go up from 5% to 9.5%. And now, thinking about the different forms of gambling now, the most addictive ones are the casino and online gambling, and then the slot machines. But of course, equally, horse racing is quite addictive. Any form of gambling can be addictive. So, well, that is where we are going to finish our discussion about simple probability in gambling. And here we've got some links, and we'll share these links with you. The Lucky Numbers and Mathsland Lottery are on the Aiming High website, and the Monty Hall problem, well, I got my pictures from Wikipedia and already acknowledged that that's where they came from. And we also showed you the video, and there's the link to the video. Now, what we are doing is providing with AIMSEC a lot more resources for you. And we'd love you to share these ideas that we are giving out. You know, we want people to know and enjoy from AIMSEC. And so there are what we call workshop guides, and for continuing professional development. And you can, or we call it collaborative professional development, you can run workshops for other teachers without having to do any planning yourself, but just using our guides. And the way it runs is you sit down together and you do the activities with the other teachers that are AIMSEC activities, and then you talk to the other teachers, they talk to you about using those activities they've just done all together, doing them in with their classes. So you can manage professional development workshops for teachers in your school or in your home area.
This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.